Hello everybody, my name is Chen from Osaka University. I'm going to present research on planning to build Soma blog using a aDual-arm robot. It's a research that we've been conducting with Professor Wei Wang and Professor Hada Kensuke, both at Osaka University. Let's start our presentation. Nowadays, products on the assembly line are very complicated. It has many parts and is difficult to assemble. To assemble these products, aDual-arm robots are widely used because of their flexibility and dexterity. But traditionally, assembly order and robot motions are decided by human experts. These are very difficult to design and error-prone. So, in this research, we focus on designing assembly planning framework to replace manual assembly planning. We expect the framework can automatically find the optimal assembly order to assemble the parts and generate additional information, for example, assembly directions and grasp poses for the motion planner. Many studies have decided assembly planning frameworks. For example, the research done by Furlow proposed a planner to pipe up the stone, and the research done by Wang introduced a framework to plan the assembly order for the Soma block. There are some limitations about the previous research. Both assume the intermediate states are stable, but for some cases, for example this one, it must contain an unstable intermediate state. The previous planners cannot work well in this case. What's more, both of these researches use polygons to analyze stability quality, but for assembly with complex contexts, for example this one, the lateral supports also need to be considered. So, in this research, we propose a planner that can autonomously refer to a second hand to support the unstable intermediate states during assembly. It is like human strategies to deal with the unstable intermediate state. And we also propose a method to evaluate stability quality based on grasp range space. This is the workflow of the entire system. The input of the system is mesh models of the parts and gripper, and the final assembly configuration. The output of the system is optimal assembly orders and directions, as well as the grasp poses for left and right hands. The grasp poses can be used for a second arm when supports from work tables and other parts are not enough to form a stable assembly. At the beginning, the permutation block generates all possible assembly orders. The system will evaluate each order to find out the optimal one. We call each subassembly in a circle as the intermediate state. 3 analyzers evaluate intermediate states in each assembly order and generate quality vectors. The stability analyzer evaluates stability of each intermediate state. The graspability analyzer evaluates the easiness of grasping the part at their final pose. The assemblability analyzer evaluates the easiness of assembling in a candidate assembly order. The assembly sequence evaluation block will use these quality vectors to find out the optimal assembly order. In addition, a system support analyzer will find out the grasp poses for the unstable intermediate state. In the following, I will introduce the details for each block. Before that, I will give 2 new terms so that the listener can more easily understand the following content. We name the part going to be assembled as the upcoming part, and the part has already been assembled as an assembled part. In this picture, we try to assemble the brown object to the purple object, so the upcoming part is the brown object, and the assembled part is the purple object. Graspability analyzer evaluates easiness of grasping the part at their goal pose by counting the number of first closed and collision-free grasp poses. For example, in the first one, there are 3 grasp poses on the upcoming part at its goal. So the grasp quality will be 3. Same as the second one, the grasp quality of it is 2. Assemblability analyzer evaluates the easiness of assembly in a candidate assembly order by measuring the clearance of optimal assembly directions to their boundaries in constraint sphere. For example, the analyzer first finds the content surfaces of the upcoming part. The normals of the content surfaces are used to create constraint spheres for finding the optimal assembly directions. The free space on the constraint sphere indicates the set of all possible assembly directions, and the optimal direction is determined as a vector with maximum clearance in the free space of the constraint sphere. In Wang's previous research, the authors classified the constraint sphere into 9 different situations and assign assemblability quality for each situation. We will use their method to assign the assemblability quality. Stability analyzer determines the stability and quality based on grasp range space. It's a method to analyze the stability of the grasp poses for an object. Here, we apply grasp range space to the Soma block assembly. We assume every vertex on content surfaces generate a uniform friction cone and use these friction cones to compute the range hole. That is the formula to compute a range hole. When a part is balanced, the range space origin should be enclosed by the range hole. The quality of the stability is computed as the minimum distance between the range space origin and the range hole surface. The distance indicates how good the forces and frictions can resist gravity. In the first example, it's an unstable assembly since a range space origin is not inside a range hole, and the second one is stable. Finally, after evaluating each assembly order, we can get 3 matrices. Each row of the matrix represents the quality for a corresponding assembly order. Every entry of a matrix is the quality for an intermediate state. This assembly sequence evaluation block finds optimal assembly order by comparing the multiplication of the worst qualities of each row. It outputs the optimal assembly order, grasp poses, and assembly directions. In addition, a system support analyzer finds assisting grasp poses to hold and support the structure if the intermediate state is unstable. These graphs are generated considering not blocking the way of assembling the next upcoming parts. Here is an example generated by the proposed assembly order planner. We can directly send this result to a motion planner we built in the previous work. The second step of the assembly is not stable and needs a second hand to support. That is the real execution of the assembly. Finally, we sum up the presentation. This work developed an assembly framework that can automatically generate the assembly order, the assembly directions, and the grasp poses for a motion planner to perform assembly tasks. The contribution of the assembly framework is that the planner can autonomously refer to a second hand to support unstable intermediate states. And we propose a method to evaluate stability quality based on grasp range space. So that's all of my presentation. Thank you for listening.